Welcome back, everyone, to the Deep Dive.
Yeah.
Today, we're going to be diving into some pretty cool AI research, specifically deep neural networks,
Oh, yeah.
or DNNs for short.
Yeah.
And we've got this research paper all about something called microdense nets.
Okay.
And the way these things work it's fascinating.
Yeah, it's pretty interesting stuff.
So we're going to be working with excerpts from this paper.
Okay.
And it does get a bit technical in places. But no worries. That's why you've got us here.
Right.
We're going to break it all down for you.
Yeah.
So we'll cover what microdense nets are, why they matter, and hopefully leave you with some, whoa, that's cool moments along the way.
Exactly.
So right off the bat, this paper tackles a big problem that DNNs have,
Oh, yeah.
which is they can be real resource hogs.
Okay.
It's like, imagine a city with tons of highways,
Yeah.
and they're all jammed up with traffic.
Yeah.
That's kind of what it's like. When a DNN is processing information,
I see.
it's slow and inefficient.
Yeah, a big part of that is the redundancy. You know, with traditional DNNs, you end up with all these multiple connections leading to the same point, creating unnecessary complexity. It's like having 5 different highways all leading to the same grocery store.
Okay, I get it. So how do microdense nets address this? The paper talks about some other DNN architectures like ResNets,
Yeah.
DenseNets. How do those fit into all this?
So ResNets and DenseNets are kind of 2 different approaches to building those highways in our city analogy. So ResNets are really good at remembering information, like a really good long-term memory.
Gotcha.
But they can get bogged down if there are too many connections. DenseNets, on the other hand, are excellent at extracting features, so picking out those crucial details from the data.
I see.
But they can get a bit too complex, like a detective trying to juggle too many clues.
Yeah, okay, so it's all about finding the right balance then. Is that where microdense nets come in?
Yeah. They try to strike that balance by using the strengths of both ResNets and DenseNets, but with a clever twist. So they introduce these things called microdense blocks for local connections and global residual learning for the longer range connections.
Okay, I'm intrigued. Break those down for me.
Okay, so imagine each microdense block as like a small, tightly knit neighborhood in our city. Within those blocks, information flows really densely and efficiently, allows the network to extract those features really effectively.
Right.
It's like having a team of experts working together on a very focused project.
I see. So then the global residual learning connects these neighborhoods together.
Right. Think of global residual learning as those expressways that connect different parts of the city.
Okay.
So it allows information to bypass certain blocks, kind of like taking a shortcut, which speeds up the processing and helps the network learn those broader patterns.
So it's like the best of both worlds.
Yeah.
Efficient local processing.
Yeah.
And fast long-range connections. Okay, I'm starting to see why these microdense nets
are so exciting. And the results really speak for themselves. This paper shows that microdense nets are achieving state-of-the-art performance on some really tough image classification tasks. They're even outperforming some of those super complex AI systems designed by, well, other AI.
Hold on. They're beating AI systems designed by AI.
Yeah.
That's pretty impressive.
Yeah.
And they're doing all this while being smaller and more efficient.
That's the amazing part. It's like building a race car that's not only incredibly fast, but also sips fuel compared to its competitors.
Okay, that's a fantastic analogy. So what's the secret? How are they achieving this level of efficiency? I know the paper dives into some pretty technical stuff like pyramidal, multi-level feature learning, and dimension cardinality adaptive convolution.
Yeah, those are some mouthful terms.
Any chance you can shed some light on those for us?
Yeah, those terms sound a little bit intimidating.
A little bit.
But basically, they allow the network to learn increasingly complex information without becoming too bulky. So think of pyramidal, multi-level feature learning as like building a pyramid. Each layer is wider than the one before it, allowing the network to process more and more complex features as you go up.
So it starts with like simple details.
Yeah.
And then it builds up.
Exactly. And then that dimension cardinality adaptive convolution ensures that each layer is kind of balanced. So no single part becomes a bottleneck, like having a well-coordinated team where everyone's pulling their weight.
Okay, that's starting to make sense. But how do we know this design actually works? Like, did they put these microdense nets?
Oh, absolutely. They ran experiments to see how they stack up against other DNNs.
Right.
One test was on something called the SciFAR data set, which is kind of a standard benchmark for image recognition.
Okay, and how did they do?
They crushed it. They outperformed several popular DNN architectures, including ResNets and mixed nets, while being significantly smaller in some cases, up to 12 times smaller.
Whoa. That's a huge difference.
Yeah.
It really challenges the idea.
It really does.
That bigger is always better when it comes to these AI systems.
They didn't stop there. They also compared micro-dense nets to networks designed using something called neural architecture search.
Oh, yeah. Or NAS. That's where AI helps design other AI, right?
Right.
So they're going up against AI-designed AI.
Yeah.
That's a pretty tough challenge.
It is. But what's really fascinating is that microdense nets were able to achieve comparable performance to these NAS-designed networks.
Really?
Even though they weren't designed using AI.
So they're holding their own against the machines designed by machines.
Yeah.
Okay. That says a lot about this approach.
Absolutely. So to really understand what's going on here, the researchers compared the microdense blocks to other building blocks used in DNNs. They really wanted to isolate what made this particular design so effective.
Yeah, what did they find?
One of the key findings was that the dense connectivity within those microdense blocks was incredibly effective at extracting features.
Makes sense. Remember those tight-knit neighborhoods we talked about?
Yeah. That close collaboration is really paying off.
But I imagine there's a limit to how much you can cram.
That's exactly what they found.
Yeah.
Into each block right, they found that. Making the dense blocks too deep actually led to diminishing returns. There's a sweet spot. Where efficiency and power meet.
So it's all about finding that right balance again.
Exactly. Too much density. And things start to get messy.
Okay.
Another important finding was the effectiveness of that pyramidal multi-level feature learning we talked about. Researchers found that this approach, combined with the dimension cardinality adaptive convolution that keeps each layer balanced, really, boosted the network's learning capabilities.
So it's like having a solid foundation and then gradually building upon it with increasing levels of expertise, making sure each layer is working at its best. That's a powerful combination.
It is. And to further confirm the power of microdense aggregation, they even compared microdense nets to some of the leading residual learning-based networks, ResNets.
Okay, and Res2Net, hold on, remind me again. ResNets are the ones that are good at remembering information, like having that good long-term memory.
Exactly, and these are like souped-up versions of ResNets.
Oh.
But guess what? Microdense nets outperformed both of them, even when they all had the same number of parameters and computational power.
So they're taking the strengths of those existing networks and they're amplifying them.
Yeah.
It's incredible how this new architecture is pushing the boundaries.
It really is. These findings have some pretty significant implications.
Okay, I've been waiting for this. Let's talk big picture implications. What kind of impact could microdense nets have on the world?
Well, imagine a world where we can deploy incredibly smart AI systems on a much wider range of devices and way more applications. Think about things like faster medical diagnosis, more personalized learning experiences, robots that can adapt and learn new tasks with ease.
Yeah, it's like taking all the things we're hoping AI can do and making them even more accessible and powerful. But this is all still in the research phase, right? What are some of the next steps for microdense nets?
Yeah, one thing they're looking at is how to further optimize microdense nets for specific tasks. So, for example, they could be tweaked to be even better at processing medical images or understanding natural language. It's about fine-tuning that balance between efficiency and power for different applications.
So it's like taking this amazing engine they've built and then customizing it for different kinds of vehicles. Like a high-performance race car needs a different setup than, say, an off-road truck.
Exactly. Another area of research is looking at how microdense nets could be implemented on even smaller devices. Imagine AI capabilities on tiny sensors or wearable technology.
Oh, that's where things get really futuristic. We're talking AI embedded in everyday objects. But we also need to think about the potential challenges, too. What about security and privacy? Are those concerns?
Yeah, those are definitely critical considerations as AI becomes more powerful. I mean, integrated into our lives, we need to be thinking carefully about the ethical implications and safeguards.
For sure.
It's not just about technological advancement. It's about responsible innovation.
Well said. It's a lot to consider, but it's an exciting time
It really is.
to be following the evolution of AI.
And this research on micro-dense nets gives us a glimpse into a future where AI is not only incredibly smart, but also incredibly efficient and accessible.
Yeah, it's a reminder that sometimes the most elegant solutions are the most powerful ones.
Absolutely.
And that about wraps it up for our deep dive into micro-dense nets. Hopefully you're leaving feeling a little bit more informed, maybe even a little inspired about what the future of AI might hold.
What are you most curious about after learning about this research?
You would love to hear your thoughts. And before we go, here's a final thought to ponder. If micro-dense nets can achieve such impressive results with fewer resources, what other breakthroughs in AI efficiency might be just around the corner?
That's a great question.
Until next time, happy diving.